Okay, I think now it's on. But what uh, what am I seeing here? I need to. Oh, okay. Okay, sorry about that. Then let me go back to the exercise. Okay, so you state the problem without any mention of concepts of graph theory, and then you represent the information with a graph. Okay, for instance, here uh, you know that you can represent this information with a graph, for instance, with 7 vertices, including another one for the exterior of the house. And the edges are the doors and all that. Okay, so you explain how to represent the information, and in your case, the graph that you get to represent the information must have between 8 and 12 vertices. Okay, and the graph must be connected, and all the vertices must have degree at least 3. Okay, then you show that the problem can be solved by finding an Eulerian path in the graph. Okay, so for instance, here is exactly this situation. You represent the information of the graph of the problem in a graph, and then you show that you can solve the problem by. Let me close the door just a minute. Okay, I'm back. So then you show that the question of whether you can go through all the doors once and only once is equivalent to finding an Eulerian path in the graph. Okay, so in your problem, you may have made a question about breaches in Königsberg, for instance. Okay, and then you show that after representing the information in the graph, the question of whether you can use all the breaches in the city once and only once is equivalent to finding an Eulerian path in the graph. Okay? And then you solve the problem with the algorithm that we have studied. You must clearly state all the steps. Okay? So this was a problem in some of the exercises for Unit 2, in which I asked you to clean up a grammar. And some people did not state all the steps. So, for instance, when you had to eliminate non-generating variables, some people just wrote the set of non-generating variables without mentioning how that was computed. Okay, so here, please state all the steps, okay? All the steps. And as a condition for me to see that you understand the algorithm, it is forbidden to obtain an initial cycle with all the edges, okay? Because if you, in the first step of the application of the algorithm, you find the final cycle, then there is only one step. Okay, so I want to see whether you understand how to apply the algorithm to each of the connected components and to join all the different cycles in the graph. Okay, you understand that? Any problem with that? Okay, so problem, okay, again without any mention of concepts of graph theory. Then you represent the information. In this case, the graph must have exactly 10 vertices. It also must be connected, and the degrees of the vertices must be at least 4. Okay? And then the problem must be solved with the concept of minimal coloring. So this is the concept that we studied in the last lecture, on Monday's lecture, in which you assign numbers to each of the vertices in the graph, and those vertices that are connected by an edge, that are joined by an edge, that are adjacent, cannot have the same number. Okay? And in the lecture, I mentioned a number of different problems that can be solved with colorings of graphs. Okay, for instance, when you need to assign resources, you need to assign, for instance, frequencies to radio stations, or class to exams, or pilots to planes, to flights, something like that. Okay, and then you connect those planes, or those exams, or those radio stations that cannot have the same resource assigned. For instance, if two radio stations are close together, they cannot have the same frequency, because then you have interference between one radio station and the other. Okay, so you represent the information with a graph, and then you solve, you show that your problem, for instance, assigning radio frequencies to radio stations, can be solved with a minimal coloring. Okay, so the minimal number of frequencies that I need is 7 or 5 or whatever. Okay, because the minimal coloring of the graph is of size 7 or 5 or whatever. And to find the minimal coloring, you can use the green program, the green app that you have studied in the lab sessions. Okay, so with this tool, you can represent, you can draw the graph in the computer, and then you have an option to find the minimal coloring of the graph. Okay, and I want a screenshot or something like that of the coloring that you have found with green. Okay. The two problems, the two exercises must be included in a single PDF file. Okay, so both exercise in the same PDF file, and you have up to Sunday, I think it's Sunday, the 24th of May at almost 12 p.m. Okay? So any question about these exercises? Yes? No? Please say yes if you understand, or something like that, for me to have some feedback. Okay? Okay. Okay. So please read the exercise, or the two exercises, carefully, and if you have any question, send me an email, or on Monday's lecture you can ask any question that you may have. Okay, of course, do not use the same exercises that we have stated in the unit worksheet, although I think that maybe the number of vertices is not the same, but well, try to do something different. Okay, you don't have to do something very, very fancy or very, very strange, but try to do something a bit different from the exercises that we have on the worksheet. Okay, any question about that? No? Okay, so let me close this. And now I closed. I lost the screen in which I had the app with the whiteboard, or not. What is this? So okay, what is? I don't think this is. Oh yeah, it's working. Oh, cool, cool. I thought it was not working, but it is. Cool. So I'm going to solve some of the exercises here. Okay, some more exercises. And I'm going to focus on exercise 16 first, and then probably exercise 15, and then some of the exercises on the tree traversals, okay? But I want to focus on exercise 16 because it's similar to what I'm asking you to solve in the exercise for unit 3, okay? So let's read the exercise, and then we try to see how to solve it, okay? So exercise 16 says that a final exam contains 7 questions, which are divided into 3 groups, okay? And these groups are the different problems that students must solve depending on whether they have passed or failed the different tests for the different units, okay? So there are 2 units, and if the student failed the first unit, he must solve problems 1, 2, and 3. If the student failed the second unit, he must solve problems 4, 5, and 6. If the student failed both units, he or she must solve problems 1, 5, and 7. Okay? So this is the statement of the exercise. Okay? And then we have to solve 2 questions. The first one is that the same teacher cannot correct more than 1 problem of the same group. Okay? Then how many teachers are needed to correct the exams? So let's focus on this question first. First, please notice that the statement of the problem, well, without this, which is of course for you to know that you have to solve it with graph theory, but the statement of the problem does not mention graphs at all, okay? Does not mention graphs at all. That is exactly what I want you to do in the exercise for unit 3, okay? So you can ask this question, this problem, to any person that you know, even if they have not taken the discrete mathematics course, okay? And then we need to represent the information. We need to represent the information. And you will see in this problem that depending on the question that you want to solve, the graph that you need may be different. Okay, so in this case, we are going to focus on this question. And this question is about assignment of resources. So how many teachers do we need to solve, to grade the exams? With the restrictions, the restriction that a person cannot correct problems from the same group, okay? So here we need to think about how to represent the information and what is the concept that we are going to use. So whenever or almost every time that you need to assign resources and you want to solve it with graph theory, it is a good idea to try to do it with a coloring, okay? Because I can represent teachers with numbers, and then I assign a number to each of the vertices, and if my restrictions are represented as connections between edges between vertices, then I will have the restriction imposed on the solution, because 2 vertices that are joined by an edge will not have the same number, will not have the same teacher. Okay, so here what I'm going to do is to represent the, let me move this to see the different restrictions. So I'm going to represent the different problems with vertices. Okay, so this is problem 1, 2, and 3. And then we have problems 4, 5, 6, and then problem 7. Okay, so these are the 7 problems. And since I want each person to correct problems that are not in the same group, then I need to join with H's those problems that are in the same group. Okay, because then when I assign numbers to the vertices, I assign teachers to the problems, then with a coloring, I impose that vertices that are connected have not the same number, have not the same teacher. Okay, so this is a natural way of translating the constraint into the graph for us to solve it with a coloring. Okay, so 1, 2, 3 are in the same group, and then 4, 5, and 6 are in the same group, and 1 is also in the same group as 5 and 7. Okay, so these are the connections that I need. Okay, do you see that? These are the connections that I need, because now when I assign a coloring, then I don't assign the same number to vertices which are connected, and then I don't assign the same teacher to problems that are in the same group. Okay? Any question with that? This is the most difficult part of the problem, because you need to choose a correct representation. Okay? You need to see that you can solve it with coloring, and then that you need to represent the problem in this way. Okay? So now we can solve the problem. In your case, in the exercises of Unit 3, you can use Green. You can use a computer tool, okay? Green or any other tool, if you want to use a different one that can find colorings in graphs, but since the one that we have used in the lab is Green, that's why I suggest to use it with Green, okay? So here it's easier because I have very, very few vertices, and they are not connected to many other vertices. Okay, so it is clear that I need to assign at least different colors to vertices that are in the same group. Okay, so of course 1, 2, and 3 must have different colors because they are all connected. Okay, now so I know that at least I need three colors. Okay, now for instance I can use red here, okay, because I cannot use green with 5 because it's connected to 1, which is green, and then for instance I can use green here. Well, it's not the same green, but let me try to find the same green. It was this one. Yes. And then blue for number 6. And then I can use either, can use also blue for 7. Okay, so in this case, just by trying, I know that at least I need 3 colors. And quickly I can find that with those 3 colors, it's enough to color the whole graph. Okay, so this is the minimal coloring. I cannot do it with less colors. Okay, but in a more complicated setting, you know that this problem is NP complete and it can be very difficult to solve. So you need the computer for that. Okay. Let me go back to the chat. Any question about this exercise? Is it understood? Okay, with a different example. Okay, almost any problem of assignment of resources will do. Okay, because you see that I need to assign teachers to correcting problems, but you can assign any other different type of resource. Okay. Okay, if there are no questions, then I'm going to move to the second part of the exercise. So let me change the whiteboard here and let's see what is the second question. Now consider that all the exams must be corrected by only one teacher, okay? But he or she must correct just one question any of the questions before moving to another correct question. Okay, so all the answers to question 1, for instance, must be solved before the person starts correcting answers for a different question, for question 4 or whatever. Okay. And also, he or she cannot correct 2 questions of the same group consecutively. Okay, so if the teacher starts correcting, for instance, question 2, then after that, he or she cannot correct question 1 or question 3. He or she must move to a different group. Okay, so in this case, we need to represent the information in a graph, and we need to think about what are the vertices, what are the edges. Here we have something that is related to using all the elements once and only once, okay? Because we need to correct all the questions once and only once, and we cannot go from certain questions to others. Okay, so we can think about solving this with either Eulerian paths or Hamiltonian paths, because in that case, if we represent the questions, the questions in the exam, the problems in the exam, as either vertices or edges, then we use all the edges or all the vertices once and only once. Okay. In this case, you can try to do it with Eulerian paths, but it may be quite complicated. It's easier if you try to solve it with Hamiltonian paths. Okay. If you represent again the information with a graph in which the questions, the problems are vertices. Okay, but now you need to connect the vertices in a different way, because now from 1, for instance, you can go not to 2 or to 3 because they are in the same group, but you can go, for instance, to 4, or you can go to 6. Okay, you cannot go to 5 or 7 because they are in the same group also. Okay, in the third group we have 1, 5, and 7. Okay, so here this is kind of the complement of the previous graph, because now we connect those vertices that are not in the same group, because I can move from one of the vertices to another one if and only if it is not in the same group. Okay, so 2 can be connected to 4, 5, 6, and 7. 3 also to 4, 5, 6, and 7. And 4, in addition to be connected to 1, 2, and 3, can be connected to 7. 5 can not be connected to 7, okay, because they are in the same group, and 6 can also be connected to 7. Okay, so again, this is the most difficult part of the exercise, because you need to think about how to represent the information, and you see that this graph is different from the one in the previous question. If we try to use the same graph, it's not helpful for this question. Okay, so the same information can be represented with different graphs depending on what is the kind of question that we need to solve, and our interest in stressing one piece of information or another. Okay, so now that we have this information in the graph, we can try to find a Hamiltonian path, a path that uses all the vertices once and only once. And remember that this is again a difficult problem. This is NP complete. It is not, there is no efficient algorithm that we know of that can check whether a given graph has a Hamiltonian path or not. Okay, so if I give you an exercise or a problem in an exam in which you have to find a Hamiltonian path, this can mean one of three things. The first thing that it can mean is that it is one of the particular cases that we have studied that always have a Hamiltonian path. We have studied that tournaments always have a Hamiltonian path, and we know of an algorithm that can solve that problem. Okay, so if it is a tournament, then you apply the algorithm. In this case, this is not a tournament, okay, because not all the vertices are connected to the others, and the graph is not directed. The second possibility is that it's easy to show that there is no such a Hamiltonian path. Okay, so for instance, if you have something like this, then uh, then it is clear in this three vertices graph, it is clear that you cannot find a Hamiltonian path, because if you start in the middle, you go to one of the sides and then you cannot go back. And if you start in one of the extremes, then you cannot go to the middle. Okay? And the third possibility, which is the one that we have here, is that it is easy to find the Hamiltonian path, because just by trying some possibilities, you will find it easily. Either because there are very few edges, and then you have to try very few possibilities, or because there are many edges, and then you can try many. You can go from many from a vertex to many others. Okay, and here we have many connections. So, for instance, we can go. I don't know. So 1, 4, 7, 6, 3, 5, and 2. Okay? But there are more possibilities. There are more possibilities. Okay? But in this case, there are many connections, so you try just some possibilities. Maybe at the first try you don't find the Hamiltonian path, but it's clear that you can find it. Okay? If the graph is much bigger and there are not so many connections or not so few connections, then the problem can be very, very difficult. Okay, but of course, I'm not going to ask you to solve one of these situations. Okay? Questions about this part of the exercise? Is it clear? Okay, no questions? Okay, so let me move then to exercise 15. In exercise 15, we are given these computers which are connected with the topology that is shown in the figure. Okay? So again, this is a valid problem, real life problem for your exercises. Okay? So we have these cities which are connected as it's shown in the figure, or we have these I don't know, these people that know each other when they are connected in the figure by one line or something like that. That is correct to use in the statement of the exercise. Okay, but you cannot say something like we have a graph with these vertices and these edges or something like that. Okay, so we are given these connections between the different computers, the 8 computers, and the first question is whether it is possible to connect all the computers without any wire crossing another. Okay, so the different cables are in a plane, are in the floor, for instance, on the floor, and they cannot cross each other. Is it possible to do that? Okay, so this question, in this case, the figure already gives us the representation of the graph. So let me copy the representation here. I'm going to copy only the the vertices so far, because for the first question I need to do something a bit different in order to solve the problem. Okay, so these are the different vertices, and now they are asking us whether it is possible to connect all the computers in the way that is given in the graph or in the figure, without the lines crossing each other. Okay, and this is exactly the definition of planarity. Okay, so what we are being asked is whether the graph is planar or not. Okay, and remember that a graph is planar if it can be drawn in the plane without crossing the edges. Okay, so in this figure, the representation is not planar, but it does not mean that the graph is not planar. If I can find another representation with the same connections in which the lines do not cross, then the graph is planar. Okay, and in this case, it can be done, for instance, by keeping these connections in the outer square or rectangle, and then, for instance, I can keep this connection. Oh, what's happening here? Okay, this connection here, this connection here, this other connection here, because they do not cross, and then I can connect B and D like this, A and E like that, and H and F in this other way. Okay, and then I have exactly the same connections, but they do not cross each other. Okay, so the graph is planar. That is exactly what we were being asked here in this question. Okay, do you understand this solution? I think it's fairly easy. The only thing that you need to notice is that they are asking us about planarity. Okay, and the second question is that due to network overloading, computers that are connected directly cannot be on at the same time. Okay, well, that is a strange condition, but let's accept it. Okay, so computers that are connected directly cannot be on at the same time. Okay, and they ask us to group computers such that computers in the same group can be turned on at the same time, and which is the minimum number of groups. Okay, so I need to find groups of computers that can be connected at the same time, and for two computers to be connected at the same time, to be on at the same time, they cannot be connected directly in the figure. Okay, so for instance, A and B cannot be on at the same time. A and H cannot be on at the same time. D and F cannot be on at the same time. So again, this is a question about coloring the graph, which is the minimum number of colors that I need in order to color this graph. Okay, if I find a way of assigning colors to the graph without assigning the same color to two vertices that are adjacent, then I have found a solution to the problem. Okay, so let's try to do that. So notice that this could be, if there were 10 vertices here and the degrees were 4 at least, this could be an exercise in your solution to the problems of Unit 3. Okay, because this is a real life problem. It's about computers and connections and groups, and you need to find a minimal coloring in order to solve it. Okay, so let's move to the whiteboard and let's try to assign colors. You can do this in your problem with green. I will do it here just by trying different possibilities, because in this case it's easy. So it's clear that I need different colors for these three vertices here, because they are connected to each other. Okay, so they cannot have the same color. Okay, and now let's try to use some with green. So I can use, for instance, green here, and then I can use, for instance, no, let's use blue here in G. Then I can use let's see, I can use blue here, and then I think I can use red here. Okay. Oh no, if I use red here, then let's use red here and then green here. Let me use green here. Is it correct? So this is correct. Let me check all the edges. Okay, so this is correct. This is correct. This is correct. This is correct. 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 Yes. 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 And yes. And yes. And yes. Okay. So this is a 3 coloring of this graph. This is a 3 coloring of this graph. Okay, you see the idea? Of course, in the exercise for Unit 3, you can do it with green. Yes, any question about this exercise? Is it clear? Yeah? Some feedback, please? Yes? Okay. So we are almost out of time. And since we have a last session on Monday, I think I will call it a day and stop here. I will send you the invitation for the meeting on Monday. We have two lectures, in fact, on Monday. One for the first seminar and one for the second seminar. So I will send 2 invitations, one for 11 o'clock, another one for 12 o'clock. And you can join the one that you like the most. Okay? I'm going to solve more or less similar exercises in both of them. I'm going to record both of them, and I'm going to upload both of them to YouTube. So please feel free to join any of them. Maybe you have another seminar at 11 or another seminar at 12. So please try to join the one that you find the most convenient. Okay? Any question? Okay, so then we'll meet again on Monday. If you have any question, please send me an email. Goodbye, everybody.